Hey guys, it's Angela Swilly, and today we're going to be talking about 9.2 absolute entropy and entropy change. You need to be able to calculate the entropy change for a chemical or physical process based on the absolute entropies of the species involved in the process. We've learned qualitatively about entropy in the last lesson, and so now we're going to learn how to quantitatively talk about entropy. And so entropy delta S, again, can be described both qualitatively and quantitatively. And we've already learned the qualitative part, and so today we're going to learn the quantitative part. Entropy can be calculated, and we have a formula that I'm going to give you. And the whole reason that we are talking about entropy is because the second law of thermodynamics states that the entropy of the universe increases for a spontaneous process and remains unchanged when a system is at equilibrium. So for a spontaneous process, the entropy of the system plus the entropy of the surroundings is going to be greater than 0. For a process at equilibrium, the entropy of the system plus the entropy of the surroundings is going to equal 0. So this is just showing you quantitatively how you would kind of think about that second law of thermodynamics. Entropy of the system. So focus on the entropy of the system, a reaction that we are studying. And when we do that, we can calculate the change in entropy for the system. The change in entropy of system is the same as the change of entropy for a reaction. And we can calculate this by adding together the standard entropies for the products multiplied by their coefficients and then repeating that for the reactants. And then you subtract the products minus the reactants. The third law of thermodynamics defines a perfect crystal at 0 Kelvin as having maximum order and an entropy value of 0. Standard entropy values are calculated depending on factors such as structure, molecular formula, modes of vibration, etc., and they are temperature dependent. The values on the next slide are standard molar entropies and refer to 1 mole at 25 degrees Celsius, which is 298 Kelvin. Now, the unit for entropy is joules per mole and per Kelvin. And that's because it's based on the number of particles present in the balanced chemical reaction, and it's also dependent upon temperature. So your units for entropy are down here, joules per moles times Kelvin. So these are standard entropies. You will not have to memorize these. These will be given to you. Now, this is our formula for how we calculate the change in entropy for a reaction. And I'm going to kind of line them up. So first of all, let's look at it as far as reactants. So here are reactants, and I'm going to kind of outline those. Not reactants, products. I'm so sorry. Here are products because we're going to do the sum of the entropy of the products minus the sum of the change in entropy of the reactants. And our reactants are right here. I need to make that a little bit. I'll do it the same as I did the other one. And they're right here. Actually, I probably need to outline both of these so that I can show you how they correlate. All right, so this is very similar to some equations we've used before and previously. So if you'll look, our number of moles right here of C is going to be multiplied right here. We get our delta S from the entropies that they give us, either, from a chart like this or from the word problem, like they'll give it to us in the word problem. So we have the Little c represents the coefficient in front of the solution, or the it's not always a solution, but of the element or of the compound of the C. So right here, this C is here, and you get the delta S of that C. So then we have the little d is the coefficient, and we're going to multiply that by the delta S of D, which is an element or a compound. And then we do the same thing with our A's and B's. We have our coefficient A, which is going to be multiplied by the delta S of element or compound A. We have our element or compound A right there. And then trying to find enough colors to make them different is tough. We have our coefficient of little b. That's going to be multiplied by the delta S of the element or compound B. Okay, so that's how we set it up, and you've done these before, so that probably was not needed, but I just want to make sure that you knew where we were getting everything from. All right, so if you want to pause this and try to do it on your own and then resume it to check it, feel free, or you can work it out with me. All right, let's go ahead and work this problem out. It says use thermodynamic data to calculate delta S for the following reaction. And it gives us the reaction, and then it also gives us the standard entropies of the different compounds. So first of all, we've got to remember that delta S equals the sum of the entropies of the products minus the sum of the entropies of the reactants. So we're going to go ahead and plug in numbers. We have 4 NO2, so I have to say 4 times NO2, and I need to do a bracket on the outside since we're using parentheses on the inside. So NO2 is 240.1. And then we add that to the other product. We have 6 moles of water, so we need to say 6 times 188.8. And these are all it tells you up there, but these are joules over moles times Kelvin, or Kelvin times mole. You can rearrange those, but all of these should have that. I just was afraid I was going to run out of room, so I'm not going to write any more of them. And then we subtract the reactants. We have 4 moles of NH3, and NH3 is 192.8 for its entropy. And then you add that to oxygen, which has 7 moles of oxygen, and oxygen's entropy is 205.2. So if you multiply these out, you get 960.4, 1132.8, 771.2, and 1436.4. Now you can put it all in your calculator. Sometimes it can get confusing though with all the different parentheses, but you're more than welcome to do that. That's how I did solve it, but this can help you eliminate some errors. And so when you add these together and then subtract them from these after they were added together, you get a delta S for the reaction that equals negative 114.4 joules per Kelvin times moles of the reaction. All right, I hope you have a great evening, and I'll see you in class.